Alright, good morning everybody. So welcome to your Friday.
Morning.
Morning. Alright, any questions on anything before we get started? Good to go. Alright. Well, so yesterday we were playing around with pipes and taking commands and putting them together on the command line, taking the output from one command, feeding it to the input of another. And we were playing a little bit with file redirection, running a command and sending the output into a file, and also running a command and reading its input from a file. And we were using these as ways to explore ideas around putting commands together, being able to do something from the command line that involves, multiple commands put together in a certain way. That's nice for a lot of one-off situations. If you want to know if you've got a process running with a certain name, you can do a ps-elf, pipe it into grep, and look for the process name. Things like that. More often, we want to do something more involved, and this is where shell scripting is going to come in. So this is mostly what we're going to talk about today is shell scripting. And not shell, but shell. Looking at ways that we can take a set of commands and put them into a file, and then by typing in that file name, have these commands executed. And a first order reason for doing that is, if you want to do the same 5 things every time that you get onto your machine, you want to check the date, you want to go into a certain directory, you want to see who's on the system, and so on. You can list those commands in a file, and then just type the name of the file, and bang, 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 each of those commands execute. But really, the bigger reason for shell scripting is that there's a whole programming environment inside Bash. We can do things with variables, we can do loops, we can do conditional statements, all the things that we do in C or Java or Python, but with one key difference, which is that in C, I can write an if statement, and what can I do in the body of that if statement if my condition is true? Well, I can do arithmetic expressions, I can call functions, I can do things like that. C-type things. In Bash, what I might do if my condition is true is compile a program, or send an email message, or push a file over to another machine somewhere out on the network. Right? So all the things that we can do from Linux, all the manipulations and analysis we can do, we can put those inside a program. And so it's a really, really rich environment for doing a lot of manipulation and control of your setup under programmed control. So we'll be talking about shell scripting, but I want to get into a topic before that, which is files and file permissions. And what actually happens when we type something into a bash shell. So if I type the word, something, and I hit enter, I get a message saying command not found. If I type a word like ls, something good happens. I get to see a listing of the files in my current directory. Or if I type the word GCC, I run the C compiler. So how does Bash know what to do in response to what I type in? Bash does not know about GCC. Okay, Bash does not know about ls. Bash does not know about the Java compiler. Bash does not know a whole lot about Linux. Okay, because at some level GCC and ls and the Java compiler are not really a part of Linux. So what do I mean by that? Bash understands a very small set of commands. It understands the command pwd, print working directory. I should show you what directory you're in. It understands the command echo, I think. If I say echo hello, it will say hello. But it really doesn't know anything about ls or C compilers or Java compilers or the editor named VI or anything like that. So when I type in something, and it happens to be one of these built-in functions like pwd, Bash will do its thing. if I type in something that bash doesn't understand, it looks for a program with that name, and if it finds it, it will execute it. So the reason I can type ls and see a list of my files is not because bash knows how to show me my files, but it finds a program named ls. And then that program executes, and that program shows me my files. So what program is happening when I say ls? I can use the command which, and it will show me, hey, when you say ls, I'm finding a program in the /bin directory named ls, and that's what I'm executing. So if I do an ls on /bin, here's all the commands that I might type that the shell will say, hey, that exists inside the bin directory. I'll go ahead and execute it. There's a fancy command called bash. Bash is a program. If I type bash, it will look inside the bin directory, find that program, and it will execute it. And you notice I'm back to prompt 2001. This is a new bash session. And if I exit this, I go back to the bash session I was in. Alright, so most times that you type something, what you're doing is you're saying, find a file with this name and run it for me. Alright, so where does bash look for these things? Well, there's a variable named path. And that variable, we'll talk about variables next. But there's a variable named bash and named path, and path is a bunch of directories separated by colons. And that's the set of directories that the shell will look in to find a command name that you just typed. Okay, really, really important. So when I type something like ls, the first thing that bash does is it looks in my directory dot. That's my current directory. And it looks to see if I have something called ls. And if I do, it will execute it. If I don't have an ls, it will look in /user/local/sbin. And if it finds a file in there called ls, it will execute that. And it's done. And it will keep searching different directories. In this case, it gets all the way down to /bin. And there it finds an ls, so that's the program that gets executed. And if it gets through all of these directories and it never finds a program with that name ls, then it will say command not found. So if I say ha ha ha, it searched all of these directories, didn't find that file, said command not found. So I could make a program in my current directory called ls.c. Right? And now if I say ls, the first thing it's going to search is my current directory. It will find my ls in there and execute it. And it does that instead of the one from /bin. And if I say which ls are you executing, it tells me I'm executing ls in your current directory. If I say where is ls, it will show me all the places where it finds anything related to ls, including /bin, /home, /nic, /ls.c. That's my source program. This is my executable program. This is the manual pages for the ls command. So if I want to run the ls from /bin, I can say /bin/ls, and now I'm doing the same thing I used to do with just ls. So this is important to keep in mind, right? There's this path of directories to search, and the first directory in which bash finds the command you just typed in, that's the one from which it will run your command. Alright, if I remove ls from my current directory and then I say ls, now it finds the one under /bin. And you can change this path. You can set this up to be whatever you like. I've got it set up for something that works for my environment, so it's the usual path, but I put the dot in the beginning, and this is set up for you also. So if you just type in the name of a program you just compiled, it will execute it from your current directory. If you don't have this dot in the beginning, then when you want to run a file, you have to say // to say, hey, run this command from my current directory. So we don't have to worry about that. And I've got some Java stuff set up, and I've got the MPLab stuff set up, and I do some Garmin programming for my bike computer, so I've got their tools set up in the path, and so on and so forth. Again, this is your environment. You can set this up however you like. If you have a directory with a lot of tools that you've developed and you want to be able to run those tools from the command line, you can put that tool directory in your path. Alright, so let me hop over to the Linux server. And let me go in my 224 directory. And let me make a scripts directory. And I'll do all of my work in here. Alright, so let me make a script called example1. And I'm going to say the date is, and I'm going to execute the date command. Alright, so when I say script1, or example1, that's the name of this file, it should find it in my current directory, and it should go ahead and say, hey, the date is, and then show me what the date is. Alright, and if I do that, I get a permission error. Alright, so it's finding this program in my current directory. It knows I want to execute it, but it's not letting me execute it. Alright, so we have to talk about file permissions. So if I do an ls-l, I get a bunch of information about my file. This is the name, this is the date it was modified, right, time and date. This is how many bytes, how many characters are in the file. There's a notion of ownership. So each person has a username. My username on the server is Nick. And this right here is telling me that this file named example1 is owned by Nick. Okay, that's because I created it. There's also a notion of a group. So you can have one or more users belong to a group. And you can associate a group with a file, and so the group that owns this file is called faculty. And I'm a member of a group called faculty. Most of you are in a group called students. Alright, why do we care about users and groups? Because of these symbols down here. Okay, these are what are called permission bits. So here's how permissions work on Linux. We have three types of people. We have the owner of a file. We have people who don't own the file but are in the same group as the group of the file. And then we have the rest of the world. And for each of these three categories, we can specify three things. Are people in this category allowed to read the file? Are they allowed to write the file? And are they allowed to execute the file? And those are the things that we're seeing when we do ls-l. Now ignore this first dash, okay? This first dash is showing me the type of file. Dash is a normal file, D is a directory, L is a link, and so on. But starting with this R, we have 9 symbols. If we have an R here, it means the owner can read the file. A W means the owner can write the file. A dash would mean the owner can execute the file. And then the next 3 symbols are the group permissions. The next 3 symbols are the world permission. Right? I have an R sitting here so I can read this file. And I have a W so I can modify it, but I can't execute it. What we want to do is we want to get an X in here to say there's execute permission. Alright, so permission bits, we think of them as binary. If there's a read permission, we put a 1. If there's a write permission, there's a 1. If there's no execute permission, we put a 0. So right now, the binary version of our permission mask looks like this. 110.000.000.000. That's octal 600. What we want is we want to give ourselves execute permission. So I want to change this to octal 700. Okay? The way we set the permission bits is change mod. So change mod, we can do what's called a bit mask, engineering 270 flashback, and then a file name. So if I say change mod 700 example 1, that should turn on this execute bit. Right, so now I've got read, write, execute. So now if I say example 1, it runs the contents of that script, which tells me the date is, and then it shows me the current date. If I set my permission bits to 0, by the way, I've said nobody has any access to this file in any way, shape, or form. And now if I try to look at the contents, it tells me permission denied. If I try to VI it, it tells me permission denied. If I set the permission bits to 400, I've got read access but not write access. So I can look at the contents, but if I try to edit it, it will tell me this is read only. So when I try to write it, it'll say read only option. Okay, so common bit mask use 755. 755 gives me full access to it as the owner. I can read, write, execute. Gives everybody else read and execute permission. But people in the group in the world can't modify it. They don't have write access. All right, let's see. Question: why wouldn't it default to you having full permissions? By default, files do not have execute permission. It's a safety measure. Because if I write, a great American novel with 5,000 lines in it, and it's called, novel, and I want to edit it, and so I say VI space novel, but I accidentally forget to type VI, and I were to just type the word novel, the shell would start executing 5,000 commands, right, which are basically random things, whatever happens to be in my novel, and that's a pretty dangerous situation. So it's kind of a safety to make sure that if you want to execute a script, you've got to set the permission to be executable. Now you can change that default so that by default everything's executable. But a few days ago I accidentally executed a file as a script that I didn't mean to, that I had permissions turned on. Didn't do any harm, but it could have. So it's a safety thing. All right, and related question on top of that, what's the point of changing permissions for that so you don't screw something up without realizing? Yeah, exactly. All right, so we do change mod 755 or 700 to our file, and now we can execute it. So let's explore this example a little bit. So echo is the command that we use for displaying a message. So I said echo the date is, and when I run this, it said the date is, and then it showed me the date. All right, so let's put a message in here. So we'll say hello, Nick. I can put blank lines in here and they don't affect anything. Okay, blank lines are ignored by bash. So I can say the date is and show me the date is. I can say your current directory is, and I can say print the working directory. I can say echo number of people on the system is, and I can do the word count command. And then I'll say goodbye. Alright, so if I run example 1, it tells me your current directory is this, the date is that, hello Nick, the number of people on the system is, and now it's just kind of sitting here, right? And it looks like my shell is broken, right? So you can always Control C. Okay, hold down Control and press C. And let's go back into our code. Well, I said the number of people on the system is, and I ran the word count command. WC reads from my keyboard, counts the number of lines when it hits the end of the file, and then prints that out. That's not what I wanted to do. What I really wanted to do was run the who command and send that into word count. So let's go ahead and run that again. And now it tells me the number of people on the system is, and I've got 8, and then 40, and then 439. All right, let's talk about comments. So, commenting is one of those things that teachers will harp on you for, okay, and I'll harp on you for it. And almost always I hear students saying something like, I'm all done with my program, all I have to do is add some comments, right? Comments are something that get put into the program at the end because your teacher said you're going to lose points if you don't have comments. Some teachers will give you a 0 if you don't have comments. I don't do that. You know, teachers like comments in your code. Why? Is it just because we like, you know, sitting back and laughing evilly as we think about our students writing comments in the middle of the night to turn in their program, right? The comments you're writing are not for me, okay? You comment your code for yourself, and you comment your code to help you write it, okay? First and foremost, it's to help you while you're writing your code. And secondly, it's to help you go back to your code later on and understand what's going on inside. So yeah, somebody said to understand your thoughts as you program. That's exactly right. Programming is a complex process. This program right here, not all that complex, okay? But a program that's, you know, 5,000 lines long and has, you know, 15 different functions in it and interacts with a bunch of other functions written in other files by other people and manages all of these different things in memory and so on and so forth. There's a lot going on, right? And it's one of the most complex environments that you're going to encounter, right? Driving your car, pretty straightforward, right? We don't need to put a post-it note saying insert key in ignition, right? We do that enough, we know exactly what we're doing. But programming, right? Writing a program to do something, you got a lot of stuff you need to keep track of. And putting comments in your code means nothing to the compiler, but it will help you keep track of what's going on. But you have to develop a commenting style that works for you, right? Just adding something at the end of a statement because you know you're supposed to have comments isn't necessarily going to help you with your programming. But as you're writing your code, be thinking about, you know, I just spent 5 minutes figuring out how to make this thing work. Maybe that's a good thing to put a comment on. Or, you know, my program's working great, but now I need to add a new feature. So right here, I'm going to put in 50 lines of code to do such and such. That's a really good thing to put in a comment, right? And write your comments for yourself. Something that's going to be meaningful to you. All right. So I'm just going to put in some silly comments here. So example of shell scripting. Let's give a greeting. Show the current date. Now this is not terribly useful commenting because, you know, I'm saying echo the date is and then I'm executing the date command. It's pretty clear what I'm doing here is I'm showing the current date. Okay? But imagine that this is 50 lines of C code, right, with variable names like x7 and k12, right? If I want to do something with my code a month from now, the first thing I have to do is reverse engineer all of that C code and figure out what the heck is this code doing so that I can go in and make changes. So a few comments will simplify that. So where am I? Okay, and how busy is the system? Now none of that has changed, anything about how the program runs. But let's take a look at this bit. The number of people on the system is, and I got this line of output. Well, remember WC, the word count program, shows you how many lines of text you have, how many words, and how many characters. So let's clean that up a little. Let's do a man on WC, and one of the first options you see, -L, print the number of new lines. Okay, print how many lines are in the file. If I want just the words, I can do -W, and if I want the number of characters, I can do -M. So WC-L will show me just the number of lines. Well, in C, if you want to try something, you have to go into your code, you have to edit it, you have to compile it, you have to run it. In Bash, since we're mainly executing Bash commands, we can do a lot of our prototyping from the command line. For example, if I just type who, and I pipe that into word count, I get my thing that I wasn't happy with. If I do who and I pipe it into word count -L, there's my symbol. There's my -H. Alright, so I'm going to go back into my editor now, and I'm going to say, let's put a -L switch. And I'm going to put a comment here. Alright, that's for my future reference. When I come back to this tomorrow or next week or 6 months from now, right, I have a little reminder for what the -L switch is. So I run that, the number of people on the system is. Alright, making sense so far? Cool. Alright, let's clean this stuff up. The date is, and then new line, your current directory is, new line, the number of people on the system is, and a new line. Let's look at the echo statement. So echo is a really simple command. It basically repeats whatever you say to it. Right? But it's got some options. And one of the more useful options is -N, do not output the trailing new line. So if I say echo hello, it actually outputs HELLO followed by a new line. And I know that because when I say echo HELLO, there's my HELLO. But my prompt for my next command didn't come right after the O, it came down here on a new line. So echo HELLO actually added a new line to the end. If I want to use pipes and I want to use XXD, I can echo hello and pipe that into XXD, and I can see it outputted ASCII characters. 68, that's an H, 65 is an E, 6C is an LL, 6F is an O, and a 0A. 0A is the ASCII code for a new line. 10th character, Control J, 10th letter of the alphabet. Alright, so we can use this -N switch. And it says, echo what I tell you to, but don't put a new line at the end. And so now it says HELLO, and at the end it just goes on to my new prompt. And if I pipe that into XXD, I only get 5 characters output, HELLO. XXD is useful for better understanding what's going on in your output sometimes. You can also throw something into a file and then VI it. But XSD is surprisingly useful. Alright, so an echo -N will print something out, but it won't automatically go down to a new line. So let's modify our example a little bit. Let's do an echo -N, the current date is, and I'll put a space there. and then let's echo dash n your current directory is, and then let's say the number of users on the system is, and then we'll say goodbye. So now we've got something that looks almost like a bit of a sophisticated program, right? Shows me the date, shows me my current directory, tells me how many people are on the system, and says goodbye. All right. Doing that in C would be really, really complex. Well, not really, really complex, but it would be fairly complex. We could do it on C pretty easily by just invoking bash commands. But if we didn't do that and we just wrote this in C, huge program, very complicated, because you have to do a lot of system calls and things like that. Bash script, it's easy, right? Because we can do all these things we do in bash, like date and who and piping things together and so on, just by typing them in. All right, let's talk about variables. If we're going to do programming in bash, we need to, in anything, we need to have variables. And this is, you know, marginally useful to be able to just do a fixed set of things by typing a single word. But really, bash starts to get powerful when we use it as a general programming environment. So one thing we got to have if we're going to do programming is variables, places to store things in memory. So in bash, a variable can be pretty much any reasonable looking thing, like I, for example. I can say I equals 10, and now I've created a variable named I, and I've set its value to 10. I don't have to declare it. I don't have to say this is an integer. I don't have to worry about scoping. I've made a variable named I, and it's equal to 10. Now if I say echo I, what is it going to show me? It's going to show me I, because echo repeats back whatever I tell it. So if we want to see the value of a variable, we use a $sign. If I say echo $I, now it shows me the value of that variable, and that's a 10. If I said I equal to 20 and I echo $I, it shows me a 20. If I said I equal to chicken and I echo $I get a chicken. So I could be an integer, it could be a floating point number, it could be a string, it could be a Boolean value. Bash doesn't see variables that way, right? It just sees a collection of characters. And when I said I equal to 10, it's really equal to a string 2 characters long, a 1 followed by a 0. That's why we don't have to specify the type, because there really isn't a type. It's just a string of symbols. So I can set I equal to 20, I equals I plus 1, echo $I. What's I equal to? It's equal to I plus 1. Why? Because that's what I said. I said I equal to the string I plus sign 1. What I really wanted was for I to take on the value 20 plus 1. Well, if I do that, I is equal to 20 plus 1. Okay, these assignment statements are extremely literal. Now, if I want to do arithmetic, there's a special syntax I can use, which is this. So I can do $, parentheses, parentheses, and then some expression, and it will actually evaluate that expression. So we can do arithmetic, but we got to do this funny notation. So now if I said I equal to 20 plus 1, and I echo I, now I is equal to 21. And now if I said I equal to $, I plus 1, and I echo I is 22. So we can do arithmetic, but we have to ask nicely, right? All right. And if I said I equal to hello, and then I said I equal to I plus 1, and then I look at the value of I, it's just 1. Why is it 1? Because trying to treat HELLO as a number didn't work. And so it said, I'm just going to treat that as a 0. And so it said I equal to 0 plus 1, which is 1. All right, so here's a cautionary tale. Bash is a little weird, okay? It's not like C, it's not like assembly language. It's way over on the other end of some spectrum of programming languages. It's on the end where it's like, it's very easy to use, it's very easy to live with, right? It's very forgiving, but it's got its own way of doing things, right? In C, if I tried to take HELLO and add 1 to it, I'd be getting, you know, seg faults and all kinds of things printing out on my screen and so on. Bash is just like, I don't know what hello is, I'll just treat it as a 0. And it doesn't even like mention anything, okay? That can be beneficial, it can be uncomfortable, okay? It depends on your perspective. For me, I resisted bash programming for a long time. I refused to do it because of things like this. It just seemed quirky, and I'll just use C, you know. When I was in college, right, I did all my programming in assembly language. Everything I did it in assembly language. Why? Because I had time and energy, and I liked assembly language. I thought it was cool. I liked the way that code looked with a bunch of hex characters in it, right? Eventually, I did everything in C for a long time, right? Now, I use bash a lot. It is so good for rapid prototyping, for putting something together really quickly, but you have to live with the fact that bash is kind of quirky in some ways, okay, things like this. But once you know its quirks, pretty easy to get along with, all right? So keep that in mind. Try to be open to the fact that, you know, it's not like C or Java or Python or assembly language. And there's upsides and downsides to that. All right, so we have variables. And we can do arithmetic on them if we want. But in general, we're just going to have a variable, and it's equal to something. If we want to get the value of the variable, we put a $sign in front. And we can do output with the echo statement. Let's talk about doing input. So input is going to use the read command. And it works like this, read X. Okay, I didn't get my prompt back, something else is going on. The system is waiting for me to type something in. So I can say hello there, and now if I look at the value of X, it's equal to hello there. All right, so read is how you can get input from the user, echo is how you can display output to the user. So let's look at example 1. I'll do an echo -n, who are you, and then I'll read your name. And then I'll say, hello, whoever name is. All right, so example 1, who are you? I am Billy Idol. And it says, hello, Billy Idol, tells me the current date, number of people on the system, says goodbye. So you can start doing some customizing like this, right? Use read to get input from a user, and it goes into that variable. And again, right, it's just a symbol. So if I say read I, and I say 23, I is equal to 23. But, you know, if I try to do arithmetic on it, I got to do the $, paren. All right, read has a bunch of options to it also. If I do a man on read, it brings up something that looks very different from what we were doing. Okay, the manual on Linux has chapters to it, and it brings up the chapter that it thinks is most relevant. So this is the read command from chapter 2. This is a low-level Unix call. Let's see if we can get the one from... Nope, can't. So read is actually built into bash. So if I go into bash, and you can search these manual pages with a slash, I could eventually come down and find the read command, but the bash pages are really big. So built-in commands. Don't really need to do this, but now I'm kind of curious. These are all the things that bash does understand. Remember I said most of what you do in bash is you run programs from other directories, but it does understand a few commands. So there's the read command. So one line is read from standard input or the file descriptor, and it saves it in a variable. And there's a lot of options you can put on here. Alright, we'll play more with read later. There's other things you can do. You can turn off the echo for passwords and things like that. Alright, so we can do input, we can do output. General programming, you need to be able to do three things. You need to be able to execute sequential instructions, you need conditionals, and you need loops. Okay, we know we can do sequential instructions because we have, you know, our example one. So let's try doing some if statements. So let's ask the person for a password. Let's read the password. Alright, so an if statement looks like this. If space, bracket, bracket, space, some condition, space, bracket, bracket, next line, then body of the if statement, closing statement of the if, which is fi, it's if spelled backwards. Okay, so then is like a curly bracket, fi is like a closing curly bracket. And if this condition is true, everything between here and here will get executed. The syntax is super critical. Okay, it's got to be if followed by at least one space, two brackets with no spaces followed by at least one space, your condition, at least one space, two brackets with no space, next line, then, next line, stuff you want to do, new line, fi. Alright, really important thing to note here. In general, especially with C programming and Java, I give you a lot of flexibility. I say code in a way that makes sense to you. If it works, I'm happy. Okay? I'm not going to do that with Bash. Bash, I'm going to insist that you write if statements exactly like this. Okay? And I'm going to insist on while loops being exactly the way that we do whiles. So it's got to be if space bracket bracket space condition space bracket bracket new line then new line body of the if statement final line fi. Okay, why am I doing that? Because Bash has lots of different ways you can write if statements. And there are times when you can write an if statement with one bracket. There are times when you can write an if statement with two parentheses. There are times when you can put the body of the if statement on the same line as the then. You can put a semicolon after this and put the word then on the same line. There's lots of different ways you can do this. My goal is to make sure that you know at least one way to do this. And the only way I can assess that is if you're writing these statements exactly the way that I'm teaching them. Otherwise, you know, you write an if statement on a test with a single bracket, and, you know, maybe because of the nature of your condition that will work. But now I have to say, did you understand that, you know, because your condition had certain characteristics, you can get away with one bracket? And do you know that in general you're going to have to use two brackets, right? And almost always, if somebody writes something different than this, even if it happens to work in that case, they got lucky, right? So I'm going to insist that when you write an if statement, you do it like this. When you write a while statement, you do it like the while statements we're doing. And that's kind of the only time I'm going to do that this year, okay? Like I say, in C and Java, usually I give you a lot of flexibility. Do something that works and we're happy. But I want to make sure that you know how to do if statements like this, This is the way I'll always do them in class. This is the way I'll always do them in sample code. Okay, so consistency is good here. All right, so let's use this. Let's see if the person knows the secret password. If bracket bracket, and I'm putting my password in quotation marks. We'll deal with reasons for that later, but it's just something we do. If $password, okay, equals equals is for comparing strings. Okay, so what's our secret password? Baseball. That's always one of the top 10 passwords that you see when people look at bad passwords. Okay, if password equals baseball, then we'll say welcome. Okay, else echo intruder alert, and we'll exit from our script. All right, and then we could do something down here that, you know, opens the secret command center or something like that. So basic test of an if statement. Enter the password, read password, so that's a variable name. If it's equal to baseball, then we'll welcome the user. Otherwise, we'll assume they don't know the password. All right, we'll make that executable. Let's go ahead and run it. So what's the password? I don't know. Okay, so intruder alert. Enter the password, baseball, and now it knows that it's me. All right, real basic example, but it gives you the essential idea. These conditions, if we're comparing strings of characters, we use equal, equal, and exclamation mark equal. This is for equal, this is for not equal. If we're comparing numbers, we use -eq, -ne, -greater than, -less than or equal to, and so on. Okay, that's also really important. Bash quirkiness. If I try to compare two strings using -eq, it may work sometimes, but it will not work all the time. If I try to compare two numbers using equal, equal, that may work sometimes, but it will not work all the time. Bash won't tell you that there's a potential problem. You've just got to know. So strings use this, numbers use this. I'm going to post something on Canvas which summarizes all of this information and stresses these kinds of things. All right, so I'm just mentioning them here. Really quickly, let's do loops. So let's do a loop. Let's initialize I to 0. Let's do a while loop. All right. So while syntax, while space, bracket, bracket, space, condition, space, bracket, bracket, do, body of the while loop, done is the closing curly bracket. My condition in this case, I want to compare two numbers. I want to compare I get its value with $i to the number 10. Numbers compare with one of these symbols, right? Greater than or equal to, less than or equal to, equal or not equal. So while I is less than or equal to 10, let's output its value, and then let's set I equal to I plus 1. All right, go ahead and run that, and there's your output. All right, I copied this code along with some other sample code from the earlier lecture onto the code area that you can get to on Canvas. So you can look at examples of this there. I will see you in 2:15 in a half hour. If you're not in that class, I will see you next week. Have a great weekend either way. Talk to you next time. Thank you.